In this video, we will start talking about Chapter 2. We will talk about the nature of light and then transition a little bit into the model of the atom, atomic orbitals, electron configurations, talk about periodic trends, and then finally how the ions are formed, so losing and gaining electrons. First, let's talk a little bit about the nature of light. Light is electromagnetic radiation, and it encompasses more wavelength than what we see in the colors. And we'll talk a little bit about that in the next slide. But let's talk a little bit about some of the characteristics of the light itself. The way we describe light as a wave, although we'll talk about light as a particle as well, but as a wave, light has, like all waves, it has a wavelength that's associated with it. We denote it with the letter lambda, and it's the distance between identical points on that wave. That could be, for example, in wave A, from crest, the top part is called a crest, from crest to crest. So you can see that this is the same point. If I start here on this crest and I reach the same point on the next crest, that is one wavelength. Wave A differs from wave B in this picture because wave B has a shorter wavelength than wave A. You can see this is a longer wavelength. The next characteristics that we're going to talk about for waves is frequency. It's denoted with the Greek letter nu. This is the number of waves that pass through a particular point in space in 1 second. So how many wavelengths, crest to crest or trough to trough, whichever point, but how many of these waves pass per second at a point in space? So let's say I start right here at the beginning and I count every second how many of these waves are passing at this point. Well, you can see since wave A has a longer wavelength, it will take shorter or fewer waves will pass this particular point than in wave B. If I'm looking at this point in wave B, because its wavelength is shorter, more waves will pass this point per second than for wave A, which leads us to this relationship between wavelength and frequency. They are inversely related. As the wavelength increases or gets longer, so longer wavelengths have lower frequencies. Shorter wavelengths have larger frequencies. This is also true with energy. So the relationship between energy and wavelength is inversely proportional as well. As the wavelength increases, the energy decreases, and vice versa. Then, since frequency and energy are both inversely related to the wavelength, they then must be directly related to each other. So a high frequency wave is a high energy wave. This is then the relationship. Shorter wavelength, higher frequency, higher energy. Longer wavelength, shorter or lower frequency and lower energy. When we talk about the electromagnetic spectrum, it encompasses all the electromagnetic radiation. And you can see here in this picture, we have all the frequencies of light, including the visible spectrum. But you can see how small a part of electromagnetic radiation is covered by the actual visible light that we are able to see. Here's another sort of review of what we mentioned in the first slide about high energy, high frequency, short wavelength. So on the one end of electromagnetic radiation, we have the gamma rays, the X-rays. These are, as you can see, the wavelength in nanometers is 10 to the minus third, 10 to the minus 1, so it's very short. They have very high frequency, 10 to the 20, 10 to the 18th, the power of 18. So these are short wavelength, very high frequency, very high energy. And we know this because gamma rays they're the most harmful to us. On the other end here, we have long wavelengths. So you can see the wavelength here. For radio waves, for example, it's 10 to the power of 11. The frequency falls, so the wavelength increased. The frequency went down to 10 to the power of 6, which means that the energy of radio waves is also low compared to gamma rays. So short wavelength, high frequency, high energy. On the other end, we have long wavelengths, smaller frequencies, lower frequency, lower energy. And then in the middle here, right about here, between ultraviolet and infrared light, we have the visible spectrum that encompasses approximately from 400 nanometers to 700 nanometer wavelength of light. Here's one more time, right? We have the visible spectrum. The higher energy, once again, it's the lower wavelength, so 400 nanometer. This is close to ultraviolet light, this high energy, high frequency, short wavelength. On the other end, we have low energy, low frequency, and high or large wavelength, 700 nanometers. Now, everything around us either has its own, so it's kind of a source of light, like the sun or a lamp, etc., or we reflect light. A few things, actually, like the sun, reflect or send off, basically emit continuous light, just like this. So this is the spectrum that we get from the sun, and we can see all the colors of the light because the sun emits white light, which encompasses all of the different colors. Other objects, including elements, atoms in the periodic table, if we see their emission spectra, so the light that they reflect off, you can see very discrete lines. You can see that this is not the same as the continuous spectrum where we see all the colors. Here we see only certain lights, and these are associated with particular wavelengths of light. Here we've got several atoms. So we have here in A, we have neon. We talked about this, that is the light from the sun. And then we've got helium, and lastly hydrogen. And you can see that we have even between atoms, the emission spectra can vary. These are not continuous. They contain discrete lines, and therefore they're called line spectra. The interesting thing about the line spectra is that every element in the periodic table has a particular emission spectrum. It's sort of like their fingerprint, and we can tell them apart. For example, if we take a spectrum of hydrogen and helium, we can see that their line spectra are different, and we can identify hydrogen, for example, by the line spectra that it has, and helium, we can tell them apart. This is one way that scientists discover what a distant star is made of. We collect the emission spectra from the distant stars, and then we can run it against known spectra of known elements, and then we can compare them, sort of like fingerprints. And then that way we can say, oh, it contains helium, or it contains hydrogen, or whatever element that we can identify. This is the way we can actually do that, because we cannot obviously travel to distant stars to figure out what their composition is. Now, in the last chapter, we talked about the atom and what the atom is made of. We talked about how it's got the nucleus and then electrons. Well, at the beginning of the 20th century, the scientists were trying to figure out how these electrons are arranged around the nucleus. And the Danish scientist Niels Bohr was one of the first to combine the line spectra and what we knew about light in his first model, his proposed Bohr model. At the time, scientists were trying to think of light in terms of these discrete packets or quanta of light, and they're known as photons. These models, so they were thinking of light in terms of particles and not as a wave, although later they figured out that light can do both. But at the time, they were thinking of light as these tiny discrete packets or these quanta of light. They're very small and they're called photons. This is what Niels Bohr then utilized to come up with his Bohr model of the atom. And here's what the model describes. He said that the electrons are orbiting around the nucleus in these series of concentric circular paths, which he called orbits. Each of these orbits has a specific energy level associated with it, and they're designated by an integer, a whole number, called the quantum number n. You can see the first orbit, which is the closest to the nucleus. If this is my nucleus, this is the first orbit. It has an n, a quantum number of 1, and that's the smallest in energy, and it's also the closest to the nucleus. N equals 2, that this orbit here has a quantum number of 2, and as you can see, it's higher in energy and further in distance than n equals 1, and so on and so forth. You can see n equals 3, 4, 5, 6, and 7, etc. Now, he studied the hydrogen atom, which is the simplest atom in the periodic table, and it only has one electron. That electron in the hydrogen atom resides in the lowest energy level in this first circle, n equals 1, which we call ground state. Ground state because it's the lowest in energy, the closest to the nucleus. If an electron absorbs energy in the form of those quantized particles that we call photons, it causes these electrons to be promoted to higher energy levels, which we call excited states. And n can be larger than 1, so 2, 3, 4, 5, 6, and 7. So going back here, if this electron in hydrogen, which is found in n equals 1, absorbs some of those photons, those tiny packets of light, it can be promoted or pushed up in energy to, let's say, the second orbit, or the third or the fourth, depending on how much light it actually absorbs. And these are then called excited states, 2, 3, 4, 5, 6, 7, for the electron of the hydrogen atom. These are all of them excited states because its ground state is n equals 1. When the electron returns to lower energy levels, it causes the atom to emit light. So if I take that electron from n equals 1 and I promote it, I give it enough energy to get to n equals 3, it's now in what we call an excited state. But it doesn't stay here forever. Eventually it gives off that light and it goes back down to its original spot. When it does that, it emits light. If the light is from n equals 3, 4, 5, and 6, So 3, 4, 5, and 6 going down to n equals 2. That corresponds to the visible spectrum. So those wavelengths, the change in these wavelengths corresponds to the part of the electromagnetic spectrum that is the visible spectrum. So we can actually see light coming from these transitions. And only from n equals 3, 4, 5, and 6 if they go back down to n equals 2. So from 3 to 2, that's one transition we can see as a color. 4 to 2, 5 to 2, and 6 to 2. Those will emit a visible spectrum, a particular light. And obviously, the smaller the change in energy, the lower the energy, the lower the frequency, the longer the wavelength, so it will be towards the red end of the spectrum, versus 6 to 2 is a higher energy gap, meaning higher frequency, shorter wavelength, so this energy transition here from 6 to 2 will be towards the violet end of the visible spectrum. This described very well, so this model described very well the electron transitions that are responsible for the hydrogen line spectrum. However, it had some flaws because it failed to explain other line spectra of other elements. And since other atoms have more than one electron, we know that hydrogen only has one, so it's the simplest, but other atoms, other elements have more than one electron, so the model must be more complex, and indeed it is much more complex than the hydrogen model, and so this has some flaws, this model. Okay, we'll do this sample problem, and then we will continue with the rest of the lecture in the next chapter or the next video. But here's the sample problem. So according to the Bohr model of the atom, indicate which of the following transitions would be expected to emit visible light. 7 to 4, 2 to 3, 5 to 2, 6 to 1, 4 to 2, 7 to 2. I will give you some time to answer this question, and we will continue the discussion in the next video session.